Okay, calculus friends, here is our lesson on increasing and decreasing functions and the first derivative test. So we can tell, or we already know, that a function is increasing when its slope is positive, aka when the first derivative is greater than 0. So you want to write all this stuff down. When we also know that a function is decreasing when the slope is negative, or being we know that slope and derivative are the same, when the first derivative is less than 0. So we have a little example to take a look at and explore those two concepts there. So what I want us to be able to do on this particular problem here, just a graph, is identify the open intervals on which the function is increasing or decreasing. So here we have your basic quadratic function, and we can see that there is a minimum point at x equals 2. And so we can see that the function is decreasing from negative infinity to 2, and we can see that it's increasing from 2 to positive infinity. And so we need to identify those intervals, and so here it is. So we have increasing, and we're going to be increasing from negative infinity to 2. And we're going to use the open interval because, well, I'll talk about that in a moment. No, I'll talk about it right now. We can see that it's not increasing there, it's decreasing. My apologies. That's decreasing from negative infinity to 2. So we can see that, just like with the ball experiment that we've done before, that when the ball goes up to its highest point, we know that it's no longer rising, but it's not yet falling either. It's kind of doing neither of those two things. So that's why at 2 we are neither increasing nor decreasing. And so we know that we're increasing from here up to here, and so that means we're increasing from 2 to infinity. And again, we're using the parentheses instead of the square brackets. Now this next problem is just a little bit more challenging, and we can see that the graph is sort of a cubic sort of function. It's got two bends in it. And we can see that the function is increasing from negative infinity all the way up until we get to right here, which is at x equals negative 2. We can see that it's decreasing, in other words, going downward as we go left to right, decreasing from negative 2 to positive 1. And we can see that it's increasing again from positive 1 up to positive infinity. And I should be going this way because we're talking about x's. So positive 1 to positive infinity x, we're increasing. So we're going to put all that information down. So we are increasing from negative infinity to negative 2. And we're also, so that's the first region, and the second region is from positive 1 to infinity. So we also have 1 comma infinity. And we know that we're decreasing, which I'm going to write up here, because I ran out of space. We know that we're decreasing only in this little region right here, just from x equals negative 2 to x equals positive 1. So we're decreasing from negative 2 to 1. And again, we're only looking at the slope here, right? The slope is positive here, so that means we're increasing. Slope is positive here, means we're increasing. Slope is negative here, means we're decreasing. And then lastly, we have this kind of semi-unusual example where we can see that the graph goes up for a while, flattens out at x equals 2, and then continues to go up again. So we can see that this graph is increasing, flattens out, and increases again. It never actually decreases. But at this point right here, it's not increasing anymore. It just kind of flattened right out. So we're going to say that this graph here is increasing from negative infinity to 2, and again from 2 to infinity. And you'll notice the curved brackets again, no square brackets, that means the 2 is not included. So that's kind of a little quick introduction on the idea or the concept of increasing and decreasing functions. So we move on to page 2. where we get a chance to discover the first derivative test. So I want to go back to our friend here, our quadratic function, and this is a negative quadratic function, you can see, because it's upside down. And we can see that there is a max point right there at 2, well, I didn't give the y value, but at x equals 2. The y value doesn't really matter right now. So we can see here that there is a max value at x equals 2. And so what I want us to do is describe the slope as we go, well, to the left of 2 and to the right of 2. So if we look back up here at the graph, we can see here's 2, and we can see to the left of 2, we can see that the slope is positive. And to the right of 2, we can see that the slope is negative. And in fact, right at 2, the slope is 0, but we're going to get to that later. But what's most important right now is that our slope goes positive and then negative. So that's what's going on right here. So describe the slope to the left and to the right of x equals 2. And so we say on the left, slope is pos. On right, slope is negative. But of course we know that slope and derivative are really the same thing. So as we go down here, I'm asking you to, or asking us to describe the derivative on the left and the right of x equals 2. And we can discover here that as we look back here, the slope is positive, therefore the first derivative is positive to the left of 2. And the slope is negative, therefore the first derivative is negative when we're to the right of 2. So we can say that f prime is greater than 0 for, well, I'll say to the left of x equals 2, and f prime is less than 0 to the right of x equals 2. And so what we see here is that we have a maximum point, and that maximum point occurs when the slope goes from positive to negative. And obviously we would have a minimum point if it was upside down, and, such as this graph right here, if we went from a slope that's going negative to a slope that's positive. So here we are, we're ready to actually write our first derivative test. And so back from our graph here, we discovered, or actually down here, we discovered that the derivative for a maximum point went from being positive, greater than 0, to being negative. So, first derivative test. If f prime changes from pos to neg, then there is a max point. So if f prime changes from positive to negative, then there is a max point. That's a then, not the. So again, if f prime changes from positive to negative, then there is a max point. And obviously you can conclude that, based on our graph right up here, that if f prime goes from negative and changes to positive, we have a minimum point. And so that we would put it right in there. So in order to use the first derivative test, we have a few steps here. So our first step is to find f prime. Our second step is to find the critical numbers. And we remember that critical numbers occur when f prime is equal to 0 or undefined. Let's not forget the undefined part. And so then the third step is to make an f prime sign chart, which we're going to do shortly. So again, our first derivative test means that we change from positive to negative for the first derivative. That means we have a maximum. Positive to negative means we have a maximum, or negative slope to positive slope, or negative first derivative to positive first derivative means we have a minimum. So let's explore a couple problems, and let's start really easy with x squared. So there it is. There's our first example right there. F of x equals x squared. And I want us to do three things. First thing is to find the critical numbers. Second thing is to find the intervals where we are increasing and decreasing. And then we want to locate the maxes and mins. And that's where we're going to do the whole sign chart thing. And I want to do this in a calculus way instead of a graphical way. So the first thing we should do is, in order to find the critical numbers, we first have to find the first derivative. So that's easy enough here. F prime of x equals 2x. And then we set 2x equal to 0. And obviously x is equal to 0. So we found our critical numbers, which is x is equal to 0. There's only one of them. And we know that f of x equals 2x is never going to be undefined, so we don't have to worry about that part. Just set it equal to 0. And then we're going to find the increasing and decreasing intervals. So we want to find out when the first derivative is positive and when the first derivative is negative. Remember, first derivative is positive means we're increasing. So what we're going to do is we're going to set up a little sign chart. And the sign chart is going to be set up with a number line. And on top of the number line, we put our critical value, or values. In this case, we only got one. And so then we're going to be talking about the numbers that are to the left of 0 and to the right of 0. Just like we did last year in pre-calc, we can set up sign charts. And over here, just like we did last year, we're going to have all of our factors of the first derivative, which in this case is simply 2x. Alright, so we're going to pick a number that's less than 0. In other words, to the left of 0, and we're going to try that into our first derivative, which is 2x right here. We're going to put it into the factors over here. So we're going to pick a number such as -1. So slap -1 in here. 2 times -1 is -2. But all we really care about is the fact that it's negative. And to the right of 0, we pick a number to the right of 0, such as +1. Put that into our factor, 2x. So 2 times +1 is +2. And again, we don't care what the value is. All we care about is the fact that the first derivative is positive when we're to the right of 0. And of course we already know this because we know that a parabola from x squared looks like this. So we expect that the first derivative is going to be negative, and then it's going to go to 0, and then it's going to be, first derivative is going to be positive. Just like we got down here. 0 to the left of 0, and, negative to the left of 0, and positive to the right of 0. And so what I like to do at this point is I like to draw in just little bits of slope so that we can get a sense about what the shape is. So we know here that the first derivative is negative, and what that means for us is that we have a slope that is downward, like this. And we know that, we already found out, that we have the first derivative equaling 0 when x is equal to 0, and we know 0 slope looks like this. So it goes straight across right there. And then we know that we have a positive slope. Our first derivative is positive, so the slope is positive when we're to the right of 0. So it looks like that. And so we can see here that we have basically a little bit of a, just kind of a rough outline of what our graph looks like. And this, of course, looks like a parabola. So we're downward this way, flat across, and then upward. And so there we see the outlines of a parabola. So we've done the critical numbers here, and we've found the increasing and decreasing regions, but we haven't actually put them in intervals yet. So actually let's put those into intervals now. So we can see that we're decreasing right here in this region all the way to 0. So we're going to be decreasing from -infinity to 0. And again at 0, it's not included. We're not increasing, we're not decreasing. It's actually just flat right there. The first derivative is equal to 0. And so we know that we're increasing when we are bigger than 0. So we can write 0 to infinity. And that's where we're increasing. And then lastly, the last bit of this is we're going to locate the max and min point. Well, that's pretty easy because it's pretty obvious that right there we're at a minimum because it's at the bottom right there. So the minimum is occurring at x is equal to 0. But of course we may be wondering what the y value is. That's easy enough. We take 0 and plug it back into the original. And 0 squared, of course, is 0. So we have a minimum point at 0, 0. Again, no big surprise. We knew all this information before we did any of this problem. So hopefully that example there will lead us right into our next example and enable you to do the next one pretty easily. So let's move on to something a little more challenging than, well, just a basic parabola, x squared. We're moving on to a parabola that is a little more complicated. So here it is, x squared plus 8x plus 10. Same tricks as before. We need to find the critical numbers, so we're going to find the first derivative first. So we got f prime of x equals 2x plus 8. And obviously setting that equal to 0, we end up with 2x plus 8 equals 0, or we find that x equals negative 4. So we go back and we do our little sign chart just like we did up here. So that means we make a little number line, put negative 4 on the number line, put the negative 4 above the number line, and we have our factor here. The only piece of our derivative is 2x plus 8, so I'm going to put that over here, 2x plus 8. Alright, so just like before, we're going to choose a number that is going to be less than negative 4, such as negative 5. Put negative 5 in there. 2 times negative 5 is negative 10, plus 8 is negative 2, but again, we don't care what the value is, just what the sign is. It's negative. And let's choose a number bigger than negative 4, such as 0. Obviously, working with 0 is always good. So put 0 in there. 2 times 0 is 0, plus 8 is positive 8, but again, don't care about the value, just the sign. And so we're able to draw in our little bit of a sketch here. So we have a negative slope, and here we have a 0 slope, and here we have a positive slope. And again, just like the previous parabola, we can see that we have a minimum point right there, but we're going to do our decreasing first. So we have we're decreasing from negative infinity to negative 4. So decreasing negative infinity to negative 4, and we are increasing when we are negative 4 to infinity. And again, we know that we have a minimum point here, and we know it's occurring at x equals negative 4, but what's the y value? We put that right back here into the original, and we get negative 4 squared is positive 16. 8 times negative 4 is negative 32. 16 minus 32 is negative 16. Plus 10 is negative 6. So we have a minimum point at negative 4, negative 6. That's our ordered pair, negative 4, negative 6. So those are our first two examples. I think they went pretty smoothly, and hopefully the rest of them will go just as smoothly. So here we have a problem that looks a little more challenging just because there's a little fraction in it, but we don't need to worry about that too much. And in case you can't read it, it says x cubed minus 3x squared plus 8x plus 1. Looks like I'm going to have to write a little bigger. So we do our first derivative again. So we have f prime of x equals, so we take the 3 and bring it down in front, which will cancel off with the 3's there, and decrease by 1, so then we end up with x squared. And the derivative of this piece right here, the negative 3x squared, is negative 6x, and the derivative of 8x is plus 8. We're just doing the power rule 3 times for that, each of the pieces there. Obviously the derivative of 1 is 0. So here we have x squared minus 6x plus 8, and again, to find the critical numbers, we're going to set that equal to 0. We don't need to worry about it being undefined because, well, it's just a quadratic and won't ever become undefined. So we have x squared minus 6x plus 8, and we're setting that equal to 0. And fortunately for all of us, this is quite factorable, and so we end up with x minus 4 and x minus 2 equals 0. So our critical numbers are 4 and 2. And what does that mean for us? That means we make our number line. And if I was a little more efficient, I would have put that over there and this one over here, but I wasn't, so that's okay though. So we'll put 2 there and 4 there. And then we're going to put in our factors, which are x minus 4 and x minus 2. I'm going to put them right over here. X minus 4, x minus 2, make them right into our sign chart. So we have our nice little sign chart right there. So, as before, we're going to pick a number to the left of 2, such as 0. Nice and easy for us. So 0 minus 4 is negative 4, so that's negative. 0 minus 2 is negative 2, so that's negative. And we know that negative times a negative is a positive. So we know the slope there is positive. So we're going to pick a number between 2 and 4, such as 3. 3 minus 4 is negative. 3 minus 2 is positive. Negative times positive is negative. And just to quickly fill these in, it's going to be positive, positive, and positive. Just trying to save a little bit of time. We're already at 20 minutes into our video here. So again, we make our little chart here, and we can see that the slope, or the derivative, is positive here. So that means we make our slope positive. And we know the derivative here is 0, so that means the slope is 0 at 2, because we found out that at 2 it's equal to 0. And then we know the slope here is negative, or the first derivative is negative, so that means the slope is negative, so we're downward like this. And here at 4, again, we're at 0, so it goes flat. And then we're positive, which means we go back up like that. Having a light flickering problem here. So we can see that we are increasing from negative infinity all the way to here. So that's increasing from negative infinity to 2. Negative infinity to 2. And we're also increasing from 4 to infinity. And we're decreasing in the other places. So we're decreasing, well, actually only right there, between 2 and 4. So we're decreasing from 2 to 4. And we can see that we have a, let's do our max and min points over here. Let's do our max point. So we have a max. And we have a max at 2. Put that back into the original problem. That's way up here. This isn't going to be as easy as I was hoping. So we're going to have 2 cubed is 8 over 3, which is 8/3. So we're just going to do a little work over on a scrap piece of paper over here. So we have 8/3. And putting 2 back into here. 2 squared is 4 times negative 3 is negative 12. So we get 8/3 minus 12. Putting the 2 back up here. 8 times 2 is 16. So plus 16. And from the original up here, it's plus 1. And then we simplify this. So we got negative 12 plus 16 is 4. Plus 1 is 5. So we have 8/3 plus 5. 5 is 15/3. That's 23/3. Or 7 2/3. So our max point occurs at 2, 7 2/3. And we would do our min point in just the same way, but I'd like to save a little bit of time, being we're at the 23rd minute. I'd like to move along to one of our later examples here. We have a bit of a chain rule problem. And after this, I think we just have 2 more. So let's do our chain rule problem right here. So again, we're going to take the first derivative. So f prime of x equals 3 times x squared minus 4 to the second power times 2x. And then we're going to multiply those 2 pieces, and we get 6x times x squared minus 4 to the second power. And we're going to set those pieces equal to 0. And we can see that we're going to get 0 for that one. And here, hopefully you're all seeing that pretty quickly, it's going to be plus and minus 2. So we're going to have a fairly busy number line here. And so we're going to have 0. And we're going to have positive 2 and negative 2. And we can see our factors here are going to be 6x and x squared minus 4 squared. And basically, anytime we have something squared, we know that it's going to be positive. So that's going to make our lives just a little bit easier. And I'm just kind of filling out the table here. So our first factor is 6x. And our second factor is x squared minus 4 squared. Which again, we know, since it's being squared, it's going to be positive all the way across. So I'm not even going to worry about taking any time to calculate those. So all we need to do is worry about the top part of the number line. So we put in negative 2 into here, so 6 times negative 2 is negative 12, so that's a negative. And between negative 2 and 0, such as negative 1, 6 times negative 1 is negative 6, so again we don't care. And between 0 and 2, such as positive 1, so put in positive 1 there. 6 times positive 1 is positive 6, so we have a positive there. And to the right of 2, such as 3, again, 6 times 3 is positive 18, so we have a positive. And so let's go down to here and finish up our table. So a negative times a positive is a negative, negative, positive, positive, because a positive times positive is a positive. And let's draw in our little slopes here. So we have a negative slope, which goes like this. And then at negative 2, we know that that means that's one of our zeros here, our critical numbers. So the slope is 0. But look here, we have a negative slope again. So it doesn't go back up, it goes down a little bit more. Kind of like that graph we looked at very early in the video here, where it kind of flattened out, but wasn't a max or a min. And then at 0, we have another critical number right there at 0. So we know we're flat here. And then we go positive. And then we go flat again, because at 2, we're having a critical number there at 2. And then we go up again. So we can see the outline of our function. It's going to be decreasing, flat, decreasing again, flat, increasing, flat, and increasing again. And I trust that we can pretty much figure out the intervals here. I'm not going to spend any time to write them down, but I will just say that we're going to be decreasing from negative infinity to negative 2. And then again from negative 2 to 0. That's our decreasing. We are increasing from 0 to 2. And then again from 2 to infinity. And here we don't have a max or a min point. It's one of those places where it just goes down, flat, and down again. So it's not a max or a min. It's just a place where the graph flattens out. We do have a min right here, however, and that's going to be at 0. Put that back into here. So we have 0 squared is 0 minus 4 is negative 4. Cubed is negative 64. So we do have here a min, and that is at 0, negative 64. That's our min point. And then again, we don't have a max here, it's just flat. So again, I'm leaving you to do the intervals of decreasing and increasing. So 2 more examples to go. So here is a problem in which we have a quotient rule. So we are again just going to set the first derivative equal to 0, but of course we know we have an x squared in the denominator, so that means we're going to have we're going to have to worry about where we are undefined. So we get f prime of x equals x squared times 1 minus x plus 3 times x over x to the 4th. Just doing our quotient rule. And cleaning things up here a little bit, we have x squared. I think I might have done something incorrect here. No, it's not x, it's 2x. So we have a 2x here. I'm just going to put the 2 out here, 2x, because the derivative of x squared is 2x. So x squared minus 2x squared minus 6x. All of that over x to the 4th. And a little cleanup here, and we get negative x squared minus 6x over x to the 4th. And that's the same as, and we're going to factor out a negative x here, so we got negative x times x plus 6 over x to the 4th. And that will be, again, just canceling off those x's, we get negative x plus 6 over x to the 3rd. Now here we have 2 factors, one on the top and one on the bottom. And whenever we have a ratio like this, or a fraction, we can find out when the fraction is equal to 0 by just looking at the numerator. So we can see the numerator is going to be equal to 0 when we're at negative 6. And it's going to be undefined Remember, we're looking for critical numbers when the first derivative is either 0 or undefined. So we're going to be undefined when x is equal to 0. So our critical numbers are x equals -6 and x equals 0. And again, we're going to put those right on our sign chart. So we got 0 here, -6 here, and we're going to fill in the rest of the sign chart with our two factors. The factors are -x plus 6, that's one of them. Remember to use the parentheses. And we got x cubed as the other factor. So we're going to pick a number less than -6, such as -7. So -7 plus 6 is -1, but that needs to be negated, so that's really going to be +1 or positive. And a number less than -6, such as -7. -7 cubed is going to be negative, and a positive divided by this time, positive divided by negative is still a negative. We're going to have to draw our sign chart on a different piece of paper. And a number between -6 and 0 we're picking, so we're going to pick -1. So -1 plus 6 is +5. Negated will be -5. And -1 cubed is still going to be negative, and a negative divided by negative is a positive. And something bigger than 0, such as 1. 1 plus 6 is 7. Negated is negative. And 1 cubed is positive, and a negative divided by a positive is a negative. And so again, we're going to get another sheet of paper here to complete our sign chart, which is going to be right here. So again, we have a negative first derivative, so we have a negative slope. Our first derivative at -6 is 0, so we're going flat across, right? 0 from up here, 0. And then our slope here is positive, because that's what the positive first derivative is. And now here at 0, we know we're undefined, because division by 0 is undefined, so I'm just going to put a little arrow like this, indicating we're undefined, division by 0. And then the slope is negative. So again, we have the outline of our graph right here, which is we have a little bit of a parabola-looking thing right here. Looks like it goes up to infinity. And then we have another bit that comes down from infinity and kind of goes off like this. So that's going to be our function. So we know that we're decreasing from, again, I'm not going to write it down in interest of saving time, -infinity to -6, we're going to be decreasing, and also decreasing from 0 to +infinity. And we're increasing from -6 to 0. And we can see, speaking of 0, right here, even if we go all the way back to the original function, when x is 0, the function is not defined there. So therefore, right here, we don't have either a maximum or a minimum. The function, again, is just not defined there at all, so there's no max and no min. We do, however, have a min right here. As we can see, it's down, flat, and up again. So our first derivative test tells us that when we are going from negative to 0 to positive, in other words, changing from negative slope to positive slope, we have a minimum. So our minimum point is going to be at -6, plugging that right in here. -6 plus 3 is -3 over -6 squared, 36. So -3 over 36 is -1/12. So our minimum point is at -6, -1/12. And there is our quotient rule problem. And again, I didn't write down the increasing and decreasing parts. And lastly, we have, you guessed it, a trig problem. Actually, this one's pretty simple. So we're going to do the first derivative. So f prime, that's the way we always start, right? F prime equals 1 plus secant squared x. And, as usual, we set it equal to 0, or undefined. So we have secant squared x plus 1 equals 0. And so we're going to subtract 1 over. So we get secant squared x equals -1. And we know that secant squared is the same as 1 over, well actually I'm going to take the square root of both sides right now. So we'll get secant of x equals, that's not good. Hold on. Really, is that what happened? 1 plus secant squared x, well that's not very good. Okay, I'm going to change my problem just slightly here. I'm going to change this to a negative so we can actually do this problem. And we'll change this to negative. And this is negative here, my apologies. And so now we got positive 1. Now we can get back to business. So secant x, taking the square root of both sides, plus and minus, equals plus or minus 1. So that means 1 over the cosine of x equals plus or minus 1. And that fraction is only going to be 1 when the cosine of x is 1 or negative 1. And that happens when we are at 90 and at when we're at 0 and at 180 and at 360. But in the directions to your problem that are going to appear in your homework, they give you an interval from 0 to 360. So 0 is not included and 360 is not included, so we're going to cross out the 0 here and the 360, so 180 is going to be the only place that we need to worry about, but we're going to turn that into radians because, well, we're in calculus and it's time to work with radians. So we are having a critical value of where we are when the first derivative is equal to 0, when we are at pi. And we're going to look here to see if we have a place at which the first derivative might be undefined, and that's right here. So 1 minus secant squared, which is the same as 1 over cosine squared x. And cosine squared x is going to be undefined when we are at pi over 2 and 3 pi over 2. So we need to have those as well. So these are our critical numbers. Pi over 2, pi, and 3 pi over 2. And so again, we do the same tricks as before. We make our number line right like this. And, oh, hey, they're actually in the order that I need them. And our factors are, we could make this into 2 factors here. We don't need this anymore. I'm just going to take this away here. So we can make 1 minus secant squared x into, actually we could just leave it as it is. We actually don't need to factor that. So we could just put that right down here. 1 minus secant squared x. So we're just going to have one big sign chart, no factors. Okay, so we're going to put in a number into 1 minus secant squared x, such as, I'm going to calculate in my brain with 45 degrees here. So less than pi over 2 is pi over 4, like 45 degrees. So we're doing the, I would definitely have to need to do this beforehand. So I'm going to leave this up to you to figure out the rest of this because I don't want to go any longer. It's already 38 minutes. So I'm going to say that what we need to do is just figure out the values of this expression here when we are less than pi over 2, when we're between pi over 2 and pi, and when we're between pi over 2 and 3 pi over 2, and then between 3 pi over 2 and 2 pi. And so we'll make our little sign diagram as we did right here, for example, when we have our slopes down and across and positive and so on. So I just want to wrap it up here. Actually, let me give you your assignment right now, which is on the back of this. So here's your assignment. It's page 186, 1 to 19, the odd ones, and then 29 and 33. Those last two are the trig ones. And I just want to remind you that our first derivative test is about this thing right here. First derivative test says if f prime changes from positive to negative, then we are at a maximum, and when f prime changes from negative to positive, we're at a minimum. So that's our first derivative test. And increasing is when the first derivative is positive. Decreasing is when the first derivative is negative. Hope you had a great time with the video, and I will see you in 2 days.